So welcome everyone to this week's Origins Colloquium. It's a great pleasure to welcome Rob Buggerow to give the talk this week. Rob is, of course, at University of Virginia. He received his PhD in 2005 from University College London, working in astrochemistry, I think, then, and went to Ohio State University as a postdoctoral fellow. And I guess came to Virginia a few years after that. Is that right, Rob?
Uh, yeah, more or less. I was in Germany a couple of years, and then I was at Cornell. But
Ah, okay, not on your department webpage.
oh,
All
okay.
right. Great. Well, anyway, it's a great pleasure to have you giving the talk today and discussion, and we'll hear about hot cores, cold chemistry and hot cores. So welcome, Rob.
Okay, great. Thanks very much for the invitation. Yeah, and thanks for the intro. Okay, so I'm going to talk about the kind of things that we do in my group. So I'm a professor in astronomy and chemistry. So we do a pretty good mixture of those two topics. My group and I are mostly computational people, right? So we do, in particular, chemical kinetics simulations. That is to say, simulate the behavior of chemistry in space as a function of time and as a function of physical conditions and so on. I'm going to talk about a particular, favorite topic of mine, which is hot cores and their chemistry, and in particular the chemistry of the more complex molecules that we find in those hot cores, in star-forming cores. What I'll show you is a mixture of work from a few years ago and also some very recent work. That work, I would say, is fair to say, very much led by Melis, certainly in terms of the sort of spectral modeling, pipeline, and all of that stuff, which I think is very exciting. But I'll sort of start off by giving you an overview of what we know about complex organic molecules in star-forming regions, and particularly what we know about how they're formed. Okay. So you might have seen a table like this in astrochemistry. It's very common to see this kind of table shown in lots and lots of talks. It's showing you, and actually this is not a very up-to-date table, but it's showing you most of, at least, the molecules that have been detected in interstellar space, as well as circumstellar regions as well. But within that interstellar denomination, we include star-forming regions as well. So there's, I'm used to saying there's almost 300 molecules detected, but it's almost 350 molecules being detected now in those regions. This table shows you the breakdown of the size of those molecules, so the number of atoms in those molecules. So there's a lot of just simple diatomic molecules, and they're pretty prevalent throughout interstellar space. And in fact, there are some rather exotic larger molecules, so highly unsaturated molecules in dark clouds and so on. But very often the kinds of molecules that we're interested in star-forming regions in particular are the larger molecules that are more highly saturated. That is to say, they have a lot of hydrogen in them. So all of these molecules, for the most part, have been detected in the gas phase through microwave rotational emission spectroscopy. Okay, that's the typical way that we detect gas phase molecules, although of course we can detect them through vibrational transitions in some cases as well. So we're talking about essentially radio telescopes, so single dish instruments like GBT, the IRAM 30 meter, and so on. But also, obviously, more modern instruments like ALMA have been responsible for detecting particularly the larger molecules that have been detected in the past few years. So as I say, most of them are gas phase molecules. Some of these molecules, really just a handful, maybe no more than a dozen, something like this, have been detected in the solid phase, by which we mean in the form of ices, right? So we know that there are dust grain particles permeating interstellar space. Ice mantles can build up on those dust grains, and we can detect those molecules through infrared absorption spectroscopy. So in other words, absorption against some background source, like a background star or a protostar, if you have an envelope of material around that protostar where the ISIS would be. Okay. What's really exciting now is that some of these more complex organics are starting to be detected with James Webb in the solid phase in these under these cold conditions. And this will be relevant as we go along. Okay, now I'm going to use this phrase complex organic molecules. Roughly half of the interstellar molecules that have been detected come under this umbrella. It's a bit vague, really, and until relatively recently, we didn't have a really clear definition. But what we try to do is sort of delineate between simple molecules from an astronomical point of view and the more complex ones. So it was decided that molecules that are carbon bearing, so organic molecules that have 6 or more atoms, are going to be known as complex organic molecules. So that will include the simplest alcohol, methanol, and a few other ones. But methanol is often considered sort of the threshold point of where we start thinking of molecules as being complex. In the interstellar medium, of course, for real chemists, this is not, none of these are really complex, right? But for astronomy, this is the case. All right. So the kind of questions that we're interested in asking in my group are how complex can those molecules get? I'm not going to touch on that so much today, but also how and when are they formed? And that's a picture that has been sort of argued about a lot over the past couple of decades, I guess you could say. And generally, we're seeing, actually, it seems that these very complex molecules may be formed even earlier than we had previously expected. So this is a commonly used figure showing sort of the general sort of star formation process from an interstellar cloud that's relatively diffuse. And then within that interstellar cloud, you'll have a denser core that will undergo gravitational collapse. You'll then reach this somewhat more advanced stage where we have an actual protostar at the center of this object. Eventually, we'll form a disk. But there'll be an envelope around this whole sort of system with the protostar at the center. That envelope will gradually be accreted onto the protostar and or onto the disk. So the envelope will get sort of thinned out as the protostar grows. But there'll be chemistry going on through this whole process. It turns out that it's in this sort of what we call hot core or hot corino stage is when those more complex organics start to become detectable in the gas phase. So until that, typically we've found that we don't detect those more complex molecules. Okay. Now I'll use these terms hot core and hot corino a little bit. Essentially, they're similar sort of stages of evolution. The hot core case is the sort of classic high mass star formation case. Hot corinos are sort of, well, I guess it's a sort of diminutive term, I guess, but used to indicate the low mass version, the solar mass type star formation version of this hot core stage, which is defined by elevated temperatures, about 100 Kelvin or more, and a complex chemistry, right? It's very rich chemistry.
So 100K is hot.
Yes, in this context, yes. So what I just showed you is the low mass case, really. Of course, in astronomy, we distinguish low mass and high mass star formation. The process of high mass star formation is somewhat different dynamically, various ways. Jonathan certainly can tell you all about that. But in terms of the physical effects relevant to the chemistry, high and low mass star formation are not so different, actually. And so what we have in the high mass case is still a situation where we're forming a protostar at the center. We've got an envelope around it. We may very likely do form a disk over time. We've got infalling material, but also we've got that growing protostar that heats its surroundings. And so what started off as cold gas and dust will be heated. And as a result, we then expect to see molecules in the gas phase. And the assumption is that a lot of that gas phase material that sort of suddenly appeared is originating on the dust grains. There's a lot of questions about how that material has formed, and in fact, whether the complex molecules are formed on the grains or whether they're formed in the gas phase through subsequent chemistry, right? But the basic picture of ices sublimating, I think, is pretty well accepted across the field. So the types of molecules that we're interested in, what we often might describe as hot core molecules, would be things like methanol, top left there. We've got oxygen-bearing molecules, we've got nitrogen-bearing species, we've got some that are carrying both. Okay, but again, very often quite highly saturated molecules, often molecules that you can buy in a bottle, you know, use in your chemistry lab. Okay, so these kinds of molecules are very often, or have been in the past, particularly associated with star formation. They haven't tended to be very prevalent in other regions. Okay, so something special about the star formation process that seems to produce these more complex organics. Okay, so I'll say just a small amount more on this. So this is the kind of spectrum that we might expect to see for a particular molecules. I'm just sort of pulling out an easy example here. Detection of urea relatively recently towards Sagittarius B2N, one of the richest, or perhaps the richest source for such molecules. So very rich spectra. We've got lots of lines, lots of features, okay? And often there are a lot of features that we actually don't have spectra for. Often thousands of emission lines are detected within the sort of microwave bands that we're looking at. So within maybe one or two ALMA bands, we might expect, you know, certainly hundreds of lines, if not thousands, some of these sources. Based on that line emission, so the analysis of the strengths of all of those lines from a particular molecule, you can determine what the excitation temperature of that molecule is, typically above 100 Kelvin. 100 Kelvin is sort of the minimum typically, and we assume that value is associated with the sublimation temperature of much of the ice. But those temperatures certainly can be a lot higher, maybe several hundred Kelvin or more. Okay, so abundances for these molecules typically, well, sometimes as low as 10 to the minus 10, but often 10 to the minus 7-ish, something like that, with respect to total hydrogen. So as I mentioned, I'll get to this in more detail as we go along, grain surface chemistry and ice chemistry are certainly implicated in the production of these more complex organics. The simpler ones, the simpler molecules, we actually have a lot of information about how they can form in the gas phase. It's not a great mystery as to how most of those are formed, but the complex ones that contain a lot of hydrogen, various reasons, are more difficult to form in the gas phase. And so we assume that grain surface and ice chemistry is involved. So as I said, there's this sublimation of the ices, but this ongoing question of whether the molecules are formed already in those ices and then sublimated, or whether simple molecules desorb from the grains, and this gas phase chemistry that leads to the formation of the larger molecules. All right, so I'll say something about what we do. Certainly we simulate chemistry during star formation. We use these chemical kinetics models, as they call, but typically rate-based models. So we calculate, or we determine chemical reaction rates. We include them in a full chemical network. And we allow the abundances of molecules to evolve as a function of time and varying physical conditions. Okay, we include both gas phase and grain surface or ice chemistry in those calculations. All right, so before I show you any sort of detail on those models, I'll point out the sort of large picture of what all the different competing mechanisms actually might be during this star formation process, and particularly, from that interstellar cloud to sort of hot core stage. So crudely speaking, think of this as a sort of evolution in time, but also a gradual increase in temperature. So throughout the whole process, there will be gas phase chemistry. Okay, and that gas phase chemistry can involve ions, neutrals, can be reactions between atoms and ions, molecules, so on. There's a whole literature on all of that gas phase chemistry. That's not so much the focus of this talk today, but it is ongoing, so please don't forget that it exists. So there's chemistry going on, but we've got dust grains too. Okay, and on those dust grains, we can adsorb gas phase material. So either the atoms or the molecules that are formed in the gas phase, they can all stick to the surfaces, and chemistry can take place on those surfaces. Particularly important aspect of that chemistry is hydrogen addition. Okay, atomic hydrogen is fairly abundant in the gas phase. Okay, and it can stick to the cold grains. And even at very low temperatures, say 10 Kelvin, or even lower in some cases, that hydrogen can still move around on the surface. Okay, so it doesn't just stick to the surface, it can actually hop around and find reaction partners. And this is one of the aspects of grain surface chemistry that makes it very different from gas phase chemistry, because the collisions take place once that particle is on the surface, and it has lots of chances to meet things. Okay, whereas in the gas phase, it's sort of a one collision, and then those two things separate. So what can happen then is that hydrogen actually can react with atoms as well as molecules and hydrogenate them. Okay, so this is one of the pieces of evidence that actually these highly saturated molecules, complex molecules that we see, do have a grain surface origin, because grain surface chemistry is particularly capable of adding hydrogen to this model. Okay, so we can form simple molecules like particularly water. We've got methanol, ammonia, and so on. And in fact, the intermediate species, the radicals, can in some cases add together as well, which I'll talk about that shortly. So as a result of this, then you build up ice mantles on the grains. And then there's still a lot that can happen. So throughout this process, as long as you've got ices, you can have UV and cosmic ray induced processing of those ices, as well as if you're dealing with small grains, stochastic heating, so UV photon being absorbed by a grain, a very small grain, could actually raise the temperature substantially. But you can have direct photolysis, radiolysis, and so on going on. As the star formation process continues, you'll heat those grains. So particularly infrared from that protostar will heat them. That can lead to the motion of surface particles more readily, but also can lead to the desorption of volatiles depending on the specific temperature. So you may get comms being formed at all of these stages as we go along. Now, of course, when the temperature really gets raised to maybe 100 Kelvin or so, depending on the species, the composition of the ices, you'll get the complete desorption of those ice mantles, and all of that stuff goes into the gas phase. Now, it could be the end of the story in terms of the formation of complex organics, but there could also be gas phase chemistry taking place as we go along. And that's, in fact, the classic picture that we had for a long time, where we assumed that it was purely gas phase chemistry that was producing all of those molecules. All right, so that's our big picture. And the question is really, what is the relative contribution of all of these different processes? And that's something that we can help to answer or start to answer with our chemical kinetics models. So I'll say something in a bit more detail about the types of chemical kinetic models that we can do. Something that we do in our group. We actually have a couple of workhorse codes that we use to simulate chemical kinetics, particularly on dust grain surfaces. One of them is called Mimic. So this is it's called a microscopic Monte Carlo kinetics model. And it's a version of this that is an off-lattice model. I won't get into all that, but what I can do is show you the type of behavior of this chemistry on a microscopic level using this type of model. Now, it's actually a bit jerky and slow on this screen. It looks a lot better on my screen. But anyway, what you can see here is an atom hopping around on the surface, doing a sort of random walk between potential minima, between binding sites on the surface. So that's the kind of motion that we expect surface particles to be doing. And once they move around and they actually meet something that they can react with, then you'll get a chemical reaction and you'll form maybe something a bit more strongly bound. And by doing this lots of times in our simulations, we can actually build up substantial ice mantles through this very often just atomic addition type of reactions that are very hard to do in the gas phase, but very easy on grain surfaces because you've got that third body involved. So the buildup of these ice mantles takes something on the order of 1 million years. Now, this type of model, Monte Carlo model, is very nice in the sense that it gives us some information about the structure of the ice. It tells us, relatively speaking, where all of the components of that ice actually are. It'd be very nice if we could use this for hot core models. Unfortunately, we can't. The computational costs for these types of models are very, very high, right? Very expensive, and they're very slow. In fact, they're very restricted in terms of the range of physical conditions that we can model. Going to higher temperatures makes it very, very intensive, essentially impossible to run these in a meaningful way for a hot core type source. So what we have to do is...
Does it matter the type of core? I mean, grade.
It does, yes. So we've done work on porosity, different porosities of grains, and that does have some effect, yeah. But so when we do hot core modeling, then we have to rely on a sort of I guess older method, and certainly a much more common method that is based on rate equations. And the difference here is that we don't get any of that local information. What we do get is population level information. So in other words, a count of the number of atoms or molecules on the grain or the number in the gas phase, but we don't know where the things are relative to each other in the ice. Okay, so we lose information. The surface diffusion rates are averages. Although these kinds of models actually are not bad representation for what the quantities we're interested in when compared to those kinetic models, microscopic models. But this type of population level model is good for complicated dynamics, or if you have physical conditions that are changing or very extreme, which is appropriate here, or for cases where we're simulating very complex chemical networks. And again, that's what we're doing. We're often looking at hundreds of species, thousands of reactions, maybe very many more.
About 10 minutes, Rob, if that's all right.
Okay, okay, sure. So I'll say a couple of things about the low temperature stuff. So what we're seeing is nowadays an evolving view of conformation, particularly where we're seeing a lot of evidence that those complex organics should be formed at low temperatures. Some of this is coming from not hot core observations, but pre-stellar core observations. So we started to see some of these more complex organics in the gas phase, even at very, very low temperatures. So we're now sort of thinking of a situation where maybe a lot of the chemistry that takes place that we see in the, molecules that we see in the gas phase in the hot period are actually formed at a much earlier stage in the interstellar cloud stage. There's increasing experimental evidence that this kind of chemistry can take place. So in other words, chemistry taking place as you build up the ices. So the addition of hydrogen to simple molecules, not just forming simple ices, but actually forming much more complex ones as well. Our picture particularly has been changing the past year or so with the advent of James Webb Telescope, where there's, let's say, at least evidence for the presence of complex organics in the ices. It is very, very difficult to fit the spectra, these absorption spectra, accurately when you have relatively weak bands. But James Webb is certainly the instrument to allow us to do that. Okay, so what I will do is just second. Show you a couple of slides. So I hope you can see that. And so what I'm going to do is show you some results from one of the models that we produced for hot cores, using an updated version of our model that allows us to simulate not just diffusive chemistry, but what we call non-diffusive chemistry. That is to say, reproducing this idea where simple molecules, not just simple molecules, but complex organics can form on dust grain surfaces. So what we see here is, those are a bit different now. Results from the chemical models showing not abundances, but rates of production. Okay, so this is a bit unusual way of showing it. What we're seeing is, if you take the top left panel there for methanol, you see the rate of production of methanol as a function of time, and with the background colors showing you the sort of crude temperature regime that we're in. Okay, so the early stages, we start to build up a lot of methanol on the dust grains through simple hydrogen addition type processes. This is entirely what we would expect. Okay. As we then go through to the warmer stage, where we sort of have our protostar and we're heating everything up, we'll desorb that methanol into the gas phase and it'll be destroyed. So that's what that blue part is showing you. The overall net production is negative, so we're destroying methanol. Okay, fine. That's pretty straightforward. What we perhaps were a little surprised to see so strongly was the production of a complex organic, this is a very common one, methylformate, at that same period when methanol is forming. Okay, so past models have had a lot of trouble reproducing that kind of behavior. The kind of changes that we've included, which I've skipped over a little bit here, but have allowed us to simulate that more accurately. So now we can simulate the production of these comps even at very low temperatures. So we've got a lot of processes going on that I'll skip through here, but we've got a range of molecules being formed through different mechanisms. It's not all grain surface chemistry, of course. There is gas phase chemistry in these models. In fact, acetaldehyde, for example, this one is one that's particularly strongly produced in the gas phase, not just on the grain. So there's a whole range of processes going on here. We've identified 5 main periods of production of comms. But a key one is that cold surface chemistry, so number 2 here. So essentially, as the ices are building up, radicals, that is to say the reactive intermediates, before you form the sort of stable molecules, those radicals can actually meet each other on the surfaces and combine, and therefore form larger molecules but there's still a lot of other chemistry going on at the same time. I know I've got a slide here that I'm going to skip through. But I'll say something about this pipeline that Melissa's been working on, and then draw some conclusions. So one thing that we've been trying to do actually for many years is improve upon the relatively simple dynamical models that we've used for a long time. So I and Professors Lee and Davis in the astronomy department have been working for some time to try to produce dynamical models that would be easily combined with the chemical models. Okay, and that's actually what we've done. We've got 2D hydrodynamic models that include protostar radiation, that's to say heating, that allow us to simulate this hot core evolution much more accurately. We then apply chemical models that are applied to Lagrangian tracer particles. So in other words, we take individual particles that are moving within the flows of these hydro models and simulate the chemistry in post-processing. The stellar work that Melissa's been doing here is to combine all this into a pipeline that gives us spectra, that gives us simulated spectra that we can combine directly or compare directly with observations. So with this picture, we end up with a sort of a 2D axisymmetric, three-dimensional picture of a hot core with all of its chemistry. So we know exactly where all the molecules are on the ices, the gas phase, and where they are distributed through that core. We can then choose a viewing angle to observe and then apply radiative transfer modeling to that and produce synthetic observations of individual lines. That gives us population diagrams. As to say, we're now doing sort of real astronomy with the simulations to get abundances. Okay. We can then get distributions of temperature, we can get column density distributions. So in other words, we can track where the molecules would be if we were doing real observations of these simulated cores. In fact, we can do ice simulations as well, or calculations of the ice column density. So we've got a lot of papers coming out on all of this. Okay, so I think, again, in the interest of time, I'm going to sort of skip to the end, and then we can, if you have questions, then I can go back to some of these slides directly. So I'll just go to my conclusions here. So the key takeaway scientifically is observations and models are both now pointing to an early cold production of these very complex organics on grains. So molecules that potentially could be important for the origin of life, if we want to really sort of extrapolate that far, those molecules are forming even before stars and planets are forming. So we're really talking about interstellar production of potentially prebiotic molecules. The process of how those molecules would be incorporated onto planets or onto planetary surfaces is a much more complicated question. We're certainly seeing those kinds of molecules being formed at very early stages, and likely without even energetic processing of those ices. So just the process of forming the ices is actually forming these quite complex organics. Okay, a bit more on the models. This treatment that we've produced not only replaces the sort of older zero-dimensional, that's in other words one single point models that we've had for this type of simulation, replaces that and gives us a framework that allows us to understand the distribution of molecules, distinguish the ages of hot cores from their masses. That's a big sort of degeneracy that we found in the observations. It's very difficult to determine exactly what the age versus mass relationship should be. We're able to sort of draw out observational effects like the viewing angle, the dust optical depth, and so on. And we've got some more advanced models coming that involve shocks and outflows in those treatments as well. The goal ultimately for all of this is to allow us to have a much more meaningful comparison between the ALMA observations and the James Webb observations. That is to say, the gas phase molecules and the solid phase molecules. Up until now, we haven't really known for sure that there were even complex organics in the ices. Now we're starting to see evidence of that. Now we can tie those observations together and try to see what the time evolution of the production of those molecules is. Okay, so I will leave it there. Thank you.
Great, thanks very much, Rob. Probably time for questions and a discussion. So Elise, maybe help me on the Virginia side, and on Zoom, just raise your hand. But maybe we can structure it a little bit. I noticed you had a slide about problems of hot cores, Rob, and perhaps you can speak a little bit. What are the limitations of the current chemical models, and are there certain rates that you need better measurements, or how uncertain are we? For example, can we predict the ratio of CO to methanol in the ice? Is that should that be an equilibrium in pre-stellar cores that we could actually predict?
Okay, so well, I wouldn't expect it to be in equilibrium in a strict chemical sense. But I think for those sort of simpler molecules, those, I think we can be quite predictive about that. I think it still is very much dependent on certain key physical conditions. So the temperature of the grains will be important for determining how much of your CO is converted to methanol. I think also there are still some open questions about the production of CO2, because the main reservoirs of carbon in interstellar ices is going to be CO and CO2. And so understanding exactly how CO2 is converted to CO is converted to CO2 there is still some detail that needs to be determined. So we're pretty good for that stuff. I think the aspects that are still not very well understood are the more energetic processing processes, so cosmic ray impacts into ices, and there's a lot going on when you have an energetic particle ripping through an interstellar ice. So you have this radiolysis process, we have electrons released. Those electrons can induce further chemistry. There's a lot we don't know about ion chemistry in ices. Most of the emphasis that we put in the past decades has been on neutral chemistry on the ices, but we have very little idea what happens when you have a full ice mantle and an ion of some kind actually attaches to that surface. There's a lot of chemistry that can happen there. So there's still things we don't know. I think CO and methanol were reasonably in good shape. I think the real bottleneck there is making sure that we have a really good physical model to make sure that the chemistry behaves itself.
Mm-hmm. But just following up on that, then, should there be a chemical clock for ices that is at least you could see a trend, or if you measure ice composition in the same, even structurally in the same pre-stellar core or different pre-stellar cores in the same region, do you think there's a hope to do a chemical clock in the ice if things are taking time to build up?
Yeah, I mean, I'm not sure that the observations such as we have them are telling us strongly that there is a large variation between ices, at least in terms of the main components of the ice. So if it's CO, CO2, that kind of thing, I'm not sure if that's necessarily it's a complicated question still, and it's very much, I think, still dependent on your ability to model the dynamics of those sources accurately.
But in your fiducial model, how long does it take to reach, for example, this business of forming methanol from the CO, this hydrogenation, is that really fast? So it happens really quickly, or are there species that are going to take 100,000 years or 1,000,000 years? to build up in the ice?
Yeah. So methanol tends to be a late time molecule, if you want to put it that way, in the ices. Um, it's dependent on the falling temperature of the grain as your collapse process takes place and the visual extinction increases and so on. But it's also a function of the removal of other species from the gas phase, so the budget essentially of gas phase species like carbon, oxygen, and hydrogen, and what their relative abundances are in the gas phase, so that when they land on the surface of your grain, you will have a different mix of those, right? And so it's the amount of hydrogen, for example, you have with respect to carbon and oxygen is going to have a strong influence on that process. So in the models, methanol tends to be formed towards the end of the model, or at least in large abundance.
Well, maybe that's something we can look for then in pre-stellar core evolution.
Sure.
So, other questions there on Virginia's side, Elise? Okay. I see Al has a comment.
Does grain size and composition affect all this very much?
The composition of the grains themselves.
Yes. Not really. I mean,
once you have an ice on the surface of the grain, then I think no.
After the ice.
But the rate at which you might kick off that ice production process could be dependent on what the grain composition is. For the grain sizes, it's not tremendously dependent on grain size.
Okay.
I think that the area where it could affect it is if you have a substantial difference in temperature between different grain sizes. But otherwise, the morphology and size of the grains doesn't have an enormous effect.
That makes sense.
Yeah. So you talk about the destruction of certain molecules only on the surface. Does it only occur on the surface of the grain, or does, like, I guess following up with the morphology question, like how does it impact the internal parts of it as those molecules are changing? Does that impact the models, or?
So you're asking what is the influence of having certain molecules being formed or destroyed on the grains rather than in the gas? Is that what you mean?
Yes.
Yes. Okay. Well, so let's say you've got simple molecules in the gas phase and they're photodissociated. So you have UV photon is absorbed by a molecule. What will happen is that you'll break that molecule typically in two. Okay. And those fragments through gas phase chemistry could eventually meet something else that they can react with. In the case of ice mantle chemistry, as soon as you photodissociate that molecule, it is surrounded by other things that it in principle could react with. Okay, so you can get an immediate reaction taking place. And so that's very different. Okay, so you don't have this bottleneck of waiting for the fragments to then meet something else in gas, because that still takes a long time, right? So that's the key thing, is you've concentrated all this material in a small area where a single UV photon actually could produce a substantial effect. It gets even more complicated when you're talking about cosmic rays, because in fact you can have a lot of individual processes all going on. If you have an energetic electron, for example, it can ionize multiple things in a sort of a small region, and all those things could react with each other.
Al Wooten has a comment or question in the chat here. I don't know, Al, if you want to just verbalize it, but otherwise I can try.
Okay, I can try. So given that temperature dependent evolution of the chemistry, which seemed to show ice-formed molecules released during warmer late evolution stages, can you differentiate the chemical origins of deuterated molecules by comparing their location and distribution in the source? ion molecule produced deuteration might differ spatially in a core from surface chemistry produced deuteration and be identified by spatial distribution. Of course, ALMA might be able to discern those spatial distributions.
Yeah, that's a good question. We don't currently have deuteration in the network that we've been using. I do have a collaboration with some people at MPE in Germany who have partially deuterated our network. And so I expect in future I'll be able to say something a bit more meaningful about it. My my suspicion is that, I mean, yes, there could be some sort of spatial differentiation in that way. That said, the gas phase deuteration is going to, well, the grain surface deuteration is still going to be strongly tied to the gas phase deuteration through that temperature behavior. So I don't know how strong of an effect it will be. You know, once you get to very low temperatures, either the gas phase chemistry is gonna deuterate molecules, but it will also result in a lot of free deuterium, neutral deuterium that will then have grain surface chemistry effects. So, but yeah, it's an open question, I think, but it's a good one.
Thank you.
Well, cosmic rays came up a few times, of course, in your talk, Rob. I mean, in the last several years, different folks have talked about protostars generating their own cosmic rays at very high levels and varying by orders of magnitude. And I don't know if you can comment on whether how certain that is and what the key diagnostics would be for your models if you boosted cosmic rays locally.
Yeah, we've done some work on this with simpler models, and in fact, in particular, going back to models where we didn't have that non-diffusive chemistry. I mean, the big effect is that beyond a certain threshold, say, well, it's time and cosmic ray ionization rate dependent. Beyond a certain threshold, you'll tend to you'll have net destruction for most of your bombs, right? So if you had a very strong ionization rate, I would expect, gas phase destruction to be very rapid, and that perhaps you would have very low abundance of comms. Now, there are sources that have low comm abundances, and there's an open question as to particularly low mass sources as to what the origin of their low mass sources sometimes will have comms and sometimes won't, and it's not immediately apparent what the difference is between those sources. I guess cosmic ray ionization rates could be an explanation. But in hot cores, I think, certainly for high mass sources, I'm not sure that we see that sort of dichotomy of hot core type sources that actually are not hot cores, don't have comms. That would be the key thing, I think. Otherwise, I think it's still difficult to distinguish, because there's a lot of chemistry that goes on even without the cosmic rays.
But then what about populations of cores in the galactic center where the cosmic ray rates again are supposed to be hundreds or thousands of times higher? Do we notice any systematic difference of hot core properties in the galactic center compared to locally?
Well, I mean, obviously, SAGE B2N is very rich in comms, right? I don't know that it's necessarily abnormally rich in the sense that we would have to invoke high cosmic ray ionization rates. I think when we try to match models to that source more carefully, I think we do tend to have a trend towards somewhat higher cosmic ray ionization rates, maybe an order of magnitude higher than the typical 10 to the minus 17. I'm not necessarily convinced that those cosmic ray ionization rates are, those high ones that are sometimes claimed, are actually appropriate in the very dense cores. That may be true for the more diffuse gas, where you're able to observe ions more easily, that you can then use for simple analysis of what cosmic ray ionization rate is. But
So no major differences then between galactic center hot cores and local ones?
I think it's likely to be more modest. Yeah.
Yeah. Yeah. Okay. Samira, you had a question. Do you want to just speak it to ask it to Rob?
Hi, Rob. Yeah. Thanks for your talk. Can you hear me?
Mm-hmm.
My question is about the anions and cations, and I saw in your slides a number of cations and anions have been detected. I wonder you take the reactivity of them into account when you do the kinetic modeling.
So in the gas phase chemistry, yes.
Okay.
I would say the gas phase chemistry is reasonably complete. Obviously, it will never be complete, but we include a large range of reactions that we expect to take place in the ISM. The issue, though, is, as I mentioned before, is ion chemistry in the ICES is not really at all considered, and is still very much an open question as to how to think about modeling it, let alone actually implementing models.
Thank you.
Is there a certain level of complexity you're hoping to get to one day, Rob? Or what is the
well, I guess I'm sort of at the level of complexity that I think it's appropriate to model at this stage. I mean, when we detect new molecules, I've often been, pushing to sort of, doing the work to include them in the chemical networks. The issue is if you go too far beyond what we've observed in the ISM, I think you just, you go too far out on a limb. There's a lot that we don't understand about the existing chemistry. And when we get to very large organics, there's a lot that we just don't know. We don't have measured even. And so we can do calculations for certain quantities. But we're constantly, every time we add a new molecule, we're constantly adding new, somewhat free parameters into the models. And so, my feeling is like when we detect the next stage of complexity of molecules in the ISM, that's the point when we should start implementing them. Yeah.
Well, I guess another question that's come up is this business of top-down, destruction of pHs and so on. Do you want to comment on other things that right now are just beyond what you can hope to do with the current framework, or do you?
Yeah, I mean, so pH is obviously a somewhat different topic. I mean, my suspicion is that the sort of these nitrile species that we've detected, so benzonitrile and a whole range of larger CN group bearing PAHs. I suspect that they and the sort of pure PAH molecules, their formation probably is more top down than bottom up. I think there are different schools of thought on this, but the fact that I think we probably do have large PAH structures being formed at the same time as dust. That seems a much more likely source for those large PAHs than building them up on dust grains or in the gas phase, atom by atom. But again, there are different schools of thought on this. I know Ralph Kaiser has ideas about forming PAHs from smaller hydrocarbons, and they may be plausible. Yeah.
Okay, we're approaching the hour now. So any last burning? Yeah, we have Rashad here. Question?
Should I just speak?
Just speak to this microphone. Yeah.
I was a bit curious about your simulations with the particles sticking on the surface and doing a random walk. Would it actually be a random walk, or would there not be any biases? with the work that
Yeah, so
well,
so I use the term random walk lightly. I mean, there certainly are biases. The potential surface on the grain, of course, is going to play a strong role in determining which direction of travel a diffuser will take, right? So it's not as if it's a smooth particle where every direction is equal. You couldn't really see very well in the video I showed because just the video response is not very good, I think. But the video actually shows quite nicely that there's actually a lot of hopping where you just go backwards and forwards between the same pair of sites, and it can take a little while before you hop out of that local minimum and into a different track, right? So the way I visualize it is that that surface actually has a sort of spider web, if you like, of low potential barrier sort of tracks where that particle can move without having to gain much energy to do that hop. There are other sites on there that will be much more difficult to reach because it's sort of jumping out of a trench, if you like, right? So you can't see that on that surface without doing the calculation, but you can certainly that's what I would expect. So it's not going to be purely random. In fact, that type of behavior does make that diffusion process a lot more complex because you can have long distance travel along these tracks, but at the same time getting out off those tracks and sort of into a very nearby region can still be very, very difficult, very slow. So yeah, it's a good question. There's a lot obviously that I can talk about today. But,
Very good. Any last burning questions for Rob on the Virginia side? So if not, let's thank Rob again for a great talk and discussion.
Thank you.